to record this, and then I'll share my screen with you. A little bit more organized than last week. There you go, you should be able to see that now. Excellent. So welcome everybody. My name is Stef Stimson, and I'm RBR's Business Development Manager for Asia Pacific, and welcome to our second APAC time-zoned webinar, and following on from Hannah's excellent presentation last week. I'm confident that you'll also enjoy today's talk by Evan Watterson of Bluecoast Consulting Engineers from Newcastle. Evan's based in Newcastle. As with last week, I'd just like to acknowledge, make acknowledgement to country, and I'm hosting this webinar from Australia, and in the spirit of reconciliation, RBR acknowledges the traditional custodians of country throughout Australia and the connections to land, sea, and community. And I pay my respects to the elders past and present, and extend that respect to all Aboriginal and Torres Strait Island peoples today. All of our webinars are recorded, and this one included, and therefore they can be hosted on our website later. As with all the previous ones we've done, I'll do about a 10-minute presentation on the RBRduet T.D that Evan's used in his research. And then I'll introduce Evan through a small interview. There will be time for questions afterwards, but you can answer them online. And I know that the president of RBR is online from Ottawa, as is Dan from the US, the technical sales manager for the US and and Canada, and I believe RBR China are on the line as well. So feel free to use the chat function as you go. So I think everybody's got their webcams off and their mics muted, which will save some bandwidth. So let's get underway. So RBR is an equipment manufacturer based in Ottawa, in Canada, and we split our product range into 4 ranges: sensors, loggers, systems, and OEM. So basically, sensors are instrumentation where there is no internal logging involved in that, and no power, and that typically will include dissolved oxygen sensors, pressure sensors, temperature sensors, etc., which go into a logger. That leads nicely into the next section, which are the loggers themselves. And you would have heard of the instruments like the RBR Virtuoso, the Duo Concerto, which are basically loggers which have internal power, they have internal memory, and they can control the sensors, log from the sensors, and output that is needed. Moving on to systems, that's basically a way of getting the data from the instrumentation to the real world. So that's through inductive modems, a Cervelo data communication buoy, which uses the data comes up through a modem to the surface and is telemetred out via Iridium or GSM, and those sorts of systems. And we also have a department that concentrates on OEM products such as the RBR Argo, which is our standard CTD, which is then installed onto Argo floats. We have a Legato CTD, which is specifically for gliders. All of our systems and sensors, loggers, and equipment we provide, we are quite obsessive about being very low power in the manufacture, so that they don't drain unnecessary power, and we can deploy them for as long as possible. So standard range you have there on the left hand side, you've got a couple of the sensors. That's a temperature and dissolved oxygen, and a temperature and depth logger. Then we move to the right. The yellow logger is a compact Solo, which is that one is a temperature logger, and they have no external comms at all on those. Then we move across from right to left. We have the Brevio, which is a compact CTD, and then the bigger version, the Concerto, which is a standard size CTD. And then with the that logger, the Concerto, as well as having CTD, you can have it in a 5 sensor body. So we have the Sputnik connector on there, and then right in the middle you have the Maestro, which can take up to 10 channels in total. So you can have CTD and PAR and fluorescence, chlorophyll, etc., etc. But that's only a fraction of what we do. And still with this image, which is very cluttered, there are a whole load of sensors which aren't included on here as well. So we have a range of loggers, sensors, OEM products, and then we tie them all together on systems such as at the bottom left, we've got the wire walker, which is a Delmar oceanographic system for using waves to power a profiler up and down a wire. We've added our inductive modem to that and low powered sensors, and we can actually provide data in real time for profiling applications without actually using any power to profile, to run the profiler. And then those who were here last week will notice I've added a new image at the bottom there as well, which is the SOFAR Oceans smart buoy and mooring, and we've been working with SOFAR to integrate our sensors into their mooring, so that you can actually, as well as having wave measurements, you can actually bring oceanographic data from the bottom to the surface through their modem and telemet it out. We're talking today of temperature and pressure. In the middle of the screen, you'll see some of the bottom middle, you'll see some of our high accuracy, low drift sensors, such as the Quartz Plus, and we also have just above there the Legato, which is a CTD that goes into the gliders. So there's a whole range of instrumentation. So today we're only talking about one very specific one, but if you need any information on any of the others, reach out to myself here in this region or one of my colleagues in the rest of the world. So Evan today is going to be talking about the RBRduet T.D, which the T stands for temperature and D for depth. It's a compact logger. It's only 27 centimeters long, and it's self-contained in terms of memory, control, and battery. The range, we have a selection of ranges in the standard form factor from 0 to 750 dbar. And then if you're starting to go deeper than that, then we've got titanium models, and they can go up to 10,000 meters or dbar. The accuracy of the sensor, similar to the Solo last week, is 0.05% of the full scale, and then the resolution is 0.001% of that. Again, because it's low power, it's a very capable sensor for long-term monitoring. And we've given some examples there. So for 1 Hertz sampling, you can get nearly 300 days of data on a single AA battery. And all those calculations are done with based on lithium thionyl chloride batteries. These loggers can take any battery chemistry at all. So for long-term projects, we recommend the lithium thionyl chloride batteries. But if you're only deploying for a week, you may look at using standard alkaline batteries, for example. Okay, so let's see the range that we have. So the standard TD, we consider it to be shallow because it's less than 1,000 meters. And standard TD comes with up to 2 Hertz sampling. With that, you can also add options of faster sampling, so 8 Hertz, 16 Hertz, even 32 Hertz sampling in that depth range. And we also have the tide and wave firmware on these loggers as well. And in actual fact, you can actually put the tide and wave averaging firmware onto the CTDs if you wish. The deeper version of it, there's a titanium version of the TD, similar sort of size, obviously titanium protection, and then we have the options with the thermistor as well, the temperature thermistor of the standard 1 second thermistor or a 0.1 second fast thermistor for rapidly changing environments, profiling, etc. Let's have a look inside the Duet. So very similar form factor. It's nice and small. If you can see my camera there, it's a nice small camera, nice small logger, sorry. and it's got a protective cover over the pressure sensor to protect it. And as you start to open up the logger, you see there's the double O-rings in there to protect it from water ingression, keep it nice and safe. As you open it wider, you've got your desiccant shown there, and the battery, and it clearly shows you which direction the battery should be installed into it. And the very clever thing is all the electronics are hidden underneath that the white part of the logger, so you can't get your dirty fingers on there, which affects sleep currents, etc., etc. So it's been designed to be as robust as possible for the use, obviously. It also has a USB connector on there, USB-C. This is exceedingly robust and it's very fast, and it also gives you true USB speeds. We've actually built the USB connector into the logger as opposed to putting an adapter on there. And then we provide the loggers with a cable. So you plug it in on one side to on the logger, and your standard USB into your computer, which opens up Ruskin, our software, and you'll see, if you can see my cursor there, your instrument will come up here with the type of instrument and the serial number. And with all RBR instrumentation, it uses a single piece of software. So Ruskin, once you've used Ruskin once for simple instrument, you can use it for all of yours as your holding grows. So as with the Solo D we talked about last week, it's a very capable logger, the Duet, but some people are exceedingly data hungry or want to do very long duration measurements. So we actually have a bigger version of this as well. So the Virtuoso, as I introduced last week, is a single channel depth logger, and the Duo, the TD, is the equivalent bigger brother or bigger sister of the Duet we're talking about today. These loggers have 8 AA batteries in there instead of the single one. And they can, instead of 60 million readings, they can cope with 240 million readings. They have twist activation as standard, so you turn the red end cap to turn it on and off. And if you require it, you can upgrade to have the Wi-Fi enabled on the body, so you can actually communicate to it through your phone, iPad, and Wi-Fi connection on your PC as well, so you don't even need to open it up on those applications. That's particularly useful for profiling instrumentation. And with these bigger loggers, you can also have external comms added to it as well. So there's a couple of end caps there shown, and with that you can have USB connectivity if it's a short distance, or RS-232/485 as per standard. So last week we talked about the top tips, and we talked about the functions in Ruskin to do auto download, auto stop, auto deploy. I won't run through that again, but if you can either watch last week's webinar on our website, or by all means get in contact with me. But this week I wanted to talk about using Ruskin as a planning tool, and this is really useful. I use it as a sales tool. When people ask me what can I do, I need a logger to do a certain thing, I can talk them through and decide which instrument is best for them. But you can also use it as a planning tool, and you don't need an instrument at all. So if you don't have an instrument yet, I encourage you to get some, of course, but this is something you can actually do by downloading Ruskin from our website. You can actually use this now and see exactly how capable this is as a tool for your research. So once you've installed it and opened it, you can go to instruments at the top. If you have an instrument, you plug it in, it automatically comes up. But in this case, would use simulate an instrument at the top. This opens up a window here, and if I'm clever with this, I should be able to turn on my laser pointer. Here we go. So at the top here, you've got the type of instrumentation you have, and legacy. It does make us sound like millennials because legacies may only be 3 or 4 years old, but that will be where your generation 2 and your very old loggers will be featured. We've got sensors, we've got the quartz, we've got the standard instruments as well, like the Virtuoso, the Duo, and the Concerto. So for this, if you wanted to run this simulation for a duet, you'd click on the compact instruments. You can see the list of all of the compact instruments here. We select the Duet T.D, and then you actually choose the options of the instrument, and I've talked about those: the Fast 8, Fast 16, etc., etc. Click OK, and you're off. It opens up. So if you had your instrument, it wouldn't have sim in front of it, but on a big one, because we're simulating the instrumentation here, we have a simulated RBRduet. It's given it a serial number, and this is a standard page where you open it up. So I'm going to get rid of that a second. So what can you change on this? Well, you can change the sampling mode on here. You can change the battery, and you can also change when you want to start. So I'll show you some examples here. Change in the sampling from 2 Hertz. It's currently 1 Hertz, and you can see that it's showing 294 days sampling. If you change that to 2 Hertz, that changes over to 57 days. So if you wanted to do some boat weight monitoring, a 2-month project with faster data, then you can still do continuous data. So that's basically 2 samples a second, every second for 57 days. That's a lot of data. With that same setting, you can change the battery chemistry here, and the lithium thionyl chloride gives maximum duration. By putting alkaline batteries in there, you can see whether this is still going to work for me. So if you're wanting to deploy it for a month, you can actually see putting alkalines in there is not going to work for you. But if you were going to do a 1-week study as an East Coast low coming into the East Coast of Australia, and you only needed to put it out for a week, you could actually do this with batteries which you buy for $8 for a pack of 10 at Bunnings at the local newsagents, etc. You wouldn't necessarily need to use the lithium thionyl chloride batteries. So it's a really good tool to use for planning. And you can do this for all of your loggers, including the Concerto with multi-sensors on there as well. So hopefully that's given you a bit of an overview. Before I introduce Evan, I'll just mention next week's webinars at 2 a.m. East Coast Australia time. There's observing beach breaching in Carmel, which Mara Oris-Scannin will be presenting on, and that's going to be very interesting one. I've seen some of the notes on that. And then, and he is my brother, but he's also very passionate about what he does. But my brother will be presenting at this time next week on tidal measurements to support hydrographic operations at the Port of Brisbane Pty Limited. So that'll be very interesting, and there'll be lots and lots of nice imagery that he has in those presentations. So thank you very much. As the contact details, sorry, there for our head office and for me, and I encourage you to contact me as you need to. So if I'm clever now, I can stop sharing that, and I can see Evan's on there. Hi, Evan. Good morning. How are you?
Good morning. How are you?
Yeah, awesome. Evan is a coastal engineer and director at Bluecoast Engineers, sorry, and he's over 15 years experience in coastal estuary, ocean and environmental engineering. I first had dealings with Evan when he was at his previous employer at Royal Haskoning, and I think that's where you probably first used RBR loggers, and I'm really pleased that you've taken that on into your new work. And I think previously you were with coastal engineering firms like Worley Parsons and Cardno Lawson Trelaw, which is great. So welcome, Evan. Thank you very much for being part of this. I have to be honest, I've looked at the photos that you have on your website, and I can't believe you get paid to do the work you do, because you work in some really amazing locations. But for those who are interested in following in similar footsteps on lovely beaches, how did you get into this field of work?
Oh, yeah, that's a good question. Well, yeah, I started a university degree in civil and environmental engineering at the University of Newcastle. And yeah, during that time, I was always interested in the physical world and then in my first year, I was a bit, disheartened by that because it felt a little bit like an extension of school, but I didn't have to go. But during that first year, I discovered that there was coastal engineering, and I didn't know it existed before that. And as soon as I heard that, I was like, yep, that's what I want to do. So I transferred down to the University of New South Wales, where they had the water research laboratory, and they had a lot of coastal engineers, like Professor Ron Cox and Bill Pearson and the likes. So I transferred down there, and also picked up a science degree in physical oceanography, and then sort of tried to forge my way into coastal. And then I started with a company called Cardno Lawson Trelaw, and I was sort of in the flood team to start with, and I kept saying, I want to do coastal, I want to do coastal. So yeah, I think they just got sick of me nagging and put me in coastal. So
excellent. Okay, well, I'm not going to hold you up too much. I do have one question for you. I'm looking for a fun fact from you that I know you've got a couple of colleagues on here, James and Heiko are on here, so maybe even they don't know. Have you got a fun fact you can share with the audience?
Well, yeah, look, I didn't lose a lot of sleep thinking about this, but I guess one thing that probably a lot of people don't know is I used to spend a lot of time skateboarding when I was younger. Even though I grew up by the beach, I spent a few years skateboarding, spent a lot of time skate parks and that sort of thing. And I guess the funny thing about that is, I've just turned 40 recently, and I've started again. So never too late.
Excellent. That youth wasn't misspent then. Clearly, if you're bringing it into your 40s, that's great. Yep. Okay. Well, if you're able to share your screen, Evan, I'll let you take it away. Thank you.
Yeah, I did just try that. It says the host disabled share screen.
Okay, let me see if I can do that. Can you do it again now?
Yeah, now it's working, yeah.
Awesome. Okay, I'll leave it to you.
Okay, no worries. I'll just get this going here, guys, because I also need to share my sound. Okay, find the right presentation. Here we go. All right, well, yeah, thanks everyone for attending today. And thanks, Stef, for organising it. Thanks to RBR for organising this. So yeah, I'm going to be presenting on some surf zone monitoring that we did at the Palm Beach Artificial Reef. That's a picture of a wave breaking over the artificial reef on the slide here. And we did this work, Bluecoast Consulting Engineers did this as a sort of internal R&D project, and with my colleagues Heiko Lur and James Lewis, and also I'd like to acknowledge Michael Thompson from the University of Queensland, who we're going to touch on a little bit of some of the stuff that Michael did. Okay, so basically, as promised in the webinar, today's discussion is going to combine these two things: there's RBR sensors and the Palm Beach Artificial Reef. Stef's given a really good introduction on the sensors and the background to those, so I'm not going to go into too much detail in that, other than to describe the application here. But I am going to talk about the Palm Beach Artificial Reef, just to give some context to the monitoring. I'm going to go through the motivations for the monitoring exercise, and I'm also going to talk about the monitoring itself and the modelling that came out of that, and then just highlight a few bits of ongoing work. So the Palm Beach Artificial Reef is located on the Gold Coast. There's a picture of it here being constructed in 2019. It's part of it's a City of Gold Coast project. It was the project in its entirety is called the Palm Beach Shoreline Project, and that included two main items: sand nourishment, which was placed in 2017. At the time, you might have seen the photos, etc., of the dredge rainbowing sand into the near shore. And then in 2 years later, in 2019, the artificial reef was constructed. And the sort of two main objectives of the artificial reef were, first and foremost, to reduce vulnerability to coastal hazards, particularly coastal erosion. Palm Beach is one of the most vulnerable beaches on the Gold Coast to coastal erosion. And the city of Gold Coast have long wanted to correct that and try and provide the best protection for properties, but also for beach amenity. So it's about trying to retain a sand buffer on the beach. And then of course there was a project back in 2004. Which there's a lot of local surfing community at Palm Beach, and they value the surf break that is there at Palm Beach currently, so the city recognised that, and one of the key objectives of the project was to increase or not adversely affect the surf amenity in the local area. So that was considered to be a sort of must-have objective. Now, hopefully I've shared our sand. I'm going to play this little video. It sort of just describes the reef. It talks a bit about the ecological impacts or benefits, which were, sort of not one of the key objectives, but one of the sort of nice added bonuses, but it also talks about the surfing.
The Palm Beach artificial reef is proving very popular not just for surfers. Divers and snorkelers are discovering a whole new world under the surface, and word is starting to spread.
Barely a few minutes swim from where the ocean meets the shore at Palm Beach. An underwater world where the Palm Beach artificial reef is teeming with sea life.
What's surprising is how quickly growth has formed on the rocks. There's a lot of small fish. Because it's great habitat, there's lots of areas for them to duck away.
The reef was installed late last year, mainly as a last-line of defence against storm surges onto the coast. A surf break, an added bonus, and now a new dive attraction from experts right the way through to beginners.
Oh, it's so close, so when it's these westerlies where the sea's flat, ideal for swimming up for a snorkel.
The reef, unlikely to stay a secret spot for long, word of mouth and the power of social media is luring divers and snorkelers from right around the country. Brendan Wolfe, 9 Gold Coast News.
Okay, so a little bit about the motivation and objectives for the monitoring exercise. As I mentioned before, it was really a Bluecoast sort of internal research and development project. We've recently completed the detailed design of an Albany artificial reef, and back in January, we were really wanting to validate some of the tools that we were going to use to design the new artificial surfing reef down in Albany. And so, given we had been involved quite heavily in the design of the Palm Beach reef, sort of through, I think we got our involvement started in around 2015, right through to the end of the construction of the artificial reef in 2019. We wanted to gather some data on the performance of the reef, so to inform the Albany reef, but also just to look at the performance of the reef for a project that we've been involved with for a long time. The reef and the nourishment works at Palm Beach as part of the Palm Beach Shoreline project has evolved over a long time, and there's been a lot of people involved. Some of the kind of evolution of the report, like the major reports that were done and designs that were done leading up to the construction and of the reef in 2019 are kind of outlined down the bottom here. It started with a WBM report with 18 options. Then in 2014, a concept design report was done by DHI, which assessed 3 options. And then The detailed design was completed in 2018 by Royal Haskoning, who we used to, some of the guys at Bluecoast used to work with. And so, yeah, that investigation included a lot of detailed design investigations, both numerical modelling and physical modelling, and construction estimates and drawings and technical specifications and the like. So yeah, I guess the take home hit from here is there's quite a lot of work went into the reef design, a lot of people involved, and you know, it was a really interesting, great project to be a part of. And I guess also we did this work in collaboration with the University of Queensland, and I guess their motivation was it was a testing ground for a novel approach to tracking breaking waves. And I guess this is kind of an area where it's a bit watch this space. Our colleagues at the University of Queensland are sort of actively working on some new techniques there. So just like to recap, to go over a few key things about the reef and what we were trying to determine with the modelling, with the monitoring exercise. So this is Palm Beach. This is a bit of a conceptual model of the processes at Palm Beach. What we have is a sort of a season. So on the left-hand side here is just the existing Palm Beach with no reef. So what we have is a seasonal varying wave climate, different in summer and winter. That wave climate is oblique to the shoreline, and that drives a longshore current and a longshore sediment transport in the order of 500,000 cubes a year. So that sediment, like as I said, that sediment transport is sort of creates a longshore drift current, and what happens with the reef is that the reef acts to sort of break up the waves. It focuses the waves towards the shallowest part of the reef where the waves break. So that takes out some of the energy, and it creates a bit of a wave shadow in the lee of the reef. On top of that, the wave breaking creates a wave-driven current and some interesting circulation patterns in the lee of the reef, which then interplay with that longshore current we talked about, and tend to sort of slow down that current. And the combination of the wave shadow and the slowing down of the longshore current is what is believed to then create a sort of a speed bump, if you like, in the longshore drift of sediment and sand, and so that's what causes the accumulation and that increased sand buffer down updrift of the reef. And in terms of the surf amenity objective of the structure, we're very interested in the wave breaking patterns occurring both over the reef itself and also in the lee. So that's in between, closer to the beach. So the exercise itself, it was completed in one day. That's actually not 100% true. We sort of did have a bit of a trial exercise that didn't go according to plan, but so yeah, we came back on the 3rd of January and completed the exercise. On that day, the waves were just under a metre and about 11 seconds, and from the east. We sort of tried to time the exercise with low tide when we would have more wave breaking over the reef. But yeah, doing anything in the surf zone, especially monitoring, is particularly difficult. So yeah, it sort of stretched out over a few more hours than we thought. So what we did was we measured waves in the lee of the artificial reef. We also measured some currents. And using a drone and video imagery, the University of Queensland did some wave tracking analysis. So what we did was we wanted to string out a couple of lines of sensors, and we used the RBRduets and a couple that we didn't have enough, so we used a couple of other sensors that will remain to be named. But yeah, here they are here. We sort of added some dive weights to them, and then we lined them all up. We had we synchronized them and set them all to the highest possible recording. I think the duos were at 16 hertz. Then we put them all on a rope, and we measured the spacing in between. We wanted them to sit a certain distance apart and have a little bit finer spacing just right in behind the reef. And so we put them all on a rope, essentially, had a buoy either side so we could see where it was. And then we basically set out on paddle boards and swimming and all sorts of things. And this is kind of a picture of us doing this here. This is us down here on one of us on the paddle board. Basically, we put a buoy over here, and then we strung our rope with all the sensors on it out in a line along here behind the reef. And as I said before, that was actually really difficult to do this, even though the waves were very small on the day. There's just a lot of current, a lot of water moving around, and bigger sets coming through, making it difficult. But having said all that, the data we got out from the RBRs was fantastic. As Steph mentioned, I've been doing metocean data collection for a while now, and I have in the past worked on some quite big projects with lots of different sensors, and I've always found the RBR sensors really reliable and robust. I mean, we set them off at Cocos Islands in some tropical conditions and left them out there for a year and got very good data capture in the tropical heat and on the reef top there. So yeah, really, I've used a lot of other sensors, water level sensors, temperature sensors, but yeah, RBRs are kind of what we've settled on. We did have 9 sensors, but 2 of them didn't work. That were not the RBRs, that were the other ones. So we had a bit of a gap in the data here. You can see these are basically the post-process waves, wave heights, or they're actually relative wave height. This on the right-hand side here is where the Palm Beach Wave Rider buoy, which I'll just go back a slide, is located just offshore. So we used the data from that, and that was kindly provided by the Queensland government. So what this plot here is showing is the relative wave height of the pattern of relative wave height measured by the RBRs in the lee of the reef, with the incoming wave height being taken from the Palm Beach Wave Rider buoy, and on the right hand side you see a directional spectra from the Palm Beach Wave Rider buoy at the time of the measurements. And as you can see, so this is a longshore transect, and you can see some pretty steep gradients in wave height that are a direct result of the wave structure interactions over the reef. So just to go back to the design a little bit, one of the things we wanted to do here was validate some of the work that had been done as part of the design, and compare the real world case to a scaled model case, which was the physical. So there was a lot of physical modelling done for the Palm Beach artificial reef. That was completed at the Queensland Government Hydraulic Laboratory and also at the Water Research Laboratory. I'm going to mostly talk about the stuff, the wave and hydrodynamic physical modelling that was done at the Queensland Hydraulic Laboratory today, because it's most relevant. But there was a lot of really good work done at WRL as well. So the objectives of that physical modelling, it's basically a scaled version of the real world structure, so the objective there was really to verify waves and currents and surf amenity outcomes of the design. It's also used to determine stable rock design, rock armour design. I'm not going to talk too much about that today, but and also sediment transport and shoreline change, which for the Palm Beach project was done mostly at WRL. So it typically involves a lot of planning. The thing I always like about physical modelling is that it's a huge amount of work that goes into it, and it's a lot of planning and a lot of construction of the model, as you can see here in these photos. Yeah, there's a lot goes into it, but as soon as you turn the wave paddle on, as soon as you start running waves, you see things straight away, and it's very intuitive, and it's an amazing tool, especially for these sort of complicated coastal engineering projects like artificial reefs. So yeah, then typically once you've built the model, you're happy with it, then you know there's a lot of testing that goes on, testing different wave conditions, water levels, and a lot of data collection that happens in the model. And then, so this picture here on the bottom right is showing some wave gauges in the lee of the artificial reef. This is actually the Albany project, but it sort of demonstrates a similar sort of thing where we had the wave gauges in behind the reef, sort of similar to where, in a similar position to where we have the RBRs in the surf zone in the 1-to-1 scale model. So yeah, so what happens is you get a lot of wave breaking over the reef that causes the attenuation of the waves. But some of the waves obviously transmits through the structure and over the top of the structure and around the structure. So it's a kind of that wave shadow is a very two-dimensional, three-dimensional sort of. Now I'm going to play this video. This is a video from the Albany project showing some of the wave breaking. Showing some of the wave breaking in the physical model. So what you see here is what waves peaking up on the, focusing over the reef, peaking up and then rolling down the crest of the structure towards the beach. You know, and yeah, for the surfers out there, they'll probably be pretty keen to get out there. So what we saw, so the top plot here is the real world 1-to-1 model. And these are the results of the measurements of the RBR sensors showing again that wave shadow. So this is where you see blue, that's a reduced wave height as compared to the offshore measurements. And red is actually an increased wave height. So as I said before, you can see these very strong alongshore variations in wave heights in the lee of the structure. And that compares, we were pretty happy with this. It compared very well with some of the results from the Queensland Hydraulics Laboratory, where that modelling was done in a 1-to-42 scale. And we had a kind of grid of sensors similar to what we did in the real world, but we had, you know, quite a big array of sensor wave gauges in the lee of that reef. So what was tested in the physical model ended up being a little bit different in terms of the shape and size of the reef. You can see that it's a little bit small, a little bit shorter than the final reef that was built, but all in all, it marries up very well with this streak of red or higher wave heights directly in the lee of the crest, and sort of a general reduction either side of the reef. We also, down the bottom here is a spectral energy plot, wave energy plot of both the wave rider buoy and a couple of the sensors in the lee of the reef. I thought particularly interesting was that was the one at A4, which shows a second peak in the wave energy spectra. The incoming wave energy spectra was just one peak, typical of a swell kind of condition. But yeah, after transforming over the reef, we see another subharmonic in the wave energy spectra. So we then use that the data from the RBR to validate the SWASH model. This SWASH model was established for the purpose of application on the Albany artificial reef, and we were really encouraged to following a round of calibration of the model. The RBR measurements are shown in this plot here, where we see wave height, significant wave height, are the blue dots there and along our longshore arrays, and the SWASH model results extracted along the same line is plotted in the blue. We were able to see that the SWASH model compared very well with the RBR measurements, and picked up that alongshore variation in wave heights. So that was great because it sort of really validated the SWASH model as a tool to use on the Albany reef. And here down in the bottom right-hand side, we see the full two-dimensional map of significant wave heights, with that wave focusing on the reef I spoke about, and these two green patches are the reduction in wave heights from that wave shadow. So we also looked at wave-driven currents. We deployed a tilt drag current meter nearby the reef. And again, we validated that and calibrated that to the SWASH model, and with good agreement, as shown in the table at the top here. So the SWASH model then provides a kind of detailed picture of the circulation patterns nearby the artificial reef, and I guess not only was this validated by the current measurements that we've taken out on the site, but also the pattern of scour that we see at the reef, and also some dye tracking and the like that was done by WRL, showing a sort of wave-driven current coming off the reef, causing other various circulations in the lee. And those currents are the currents that then interact with the longshore current and cause the slowing of the longshore current and potentially some accumulation of sediment. So the third thing that was done was some hydrographic survey. The guys from Sand Maps undertook a trial exercise as part of this, and this was taken shortly after the large swell that was that occurred with associated with TCUSC in early February. And so this is the high resolution bathymetric survey in the picture here. And one thing that was interesting was this scour hole that was observed as a result of those wave-driven currents, particularly after that large swell event. And so this shows a couple of comparisons to some other surveys. That the left-hand side shows a comparison to the as-constructed survey, where we mostly see over the reef, it's mostly white, not much change. But then we see in the lee that large sour hole in the blue. Blue is erosion, and red is accretion. Interesting accretion feature over here on the northern side of the reef. And then this is a picture of a subsequent survey undertaken following the 18th of February. And you can see a little bit that scour hole here is starting to fill in. But yeah, generally. So, and I guess the fourth thing was to look at wave breaking and look at surf amenity. We had obviously been looking at surf amenity and just getting some general drone footage, and this shows this video is from actually not long after the construction was finished. So we already had a bit of a feel that there was, you know, some good surfing waves occurring over the reef. But, you know, as, you know, scientists and engineers, we want to have a bit more scientific approach to that. And the surfing community can always also be very, yeah, they have varying opinions. So yeah, we wanted to have a bit of a look at the wave breaking and whether the wave breaking over the reef was conducive to surf amenity, to that project objective. So there in the field, there was we used a drone to record some videos. The wave tracking technique was then applied to derive wave breaking tracks and data, and that was compared to the swash model. So the swash model is shown. This is some pictures of these darker areas of the wave crests. You can see the waves bending and over the reef. This is kind of where the surfing would take place here. These pictures on the right highlight just areas where wave breaking has happened. So we were trying to compare that swash model and pattern of wave breaking with what was observed through the eyes of the camera and subsequent data analysis by UQ. And when we compared those two things, these are the results here. So again, the modelled and the observed were comparable. They showed maximum ride lengths of up over 100 metres. So, you know, good wave breaking durations. And even though the conditions were quite small on the day, there was still around 2 surfable waves occurring a minute. So I guess that kind of wraps up the surf zone monitoring and modelling that we undertook for the Palm Beach Reef recently. So we really used it to validate numerical and wave and flow models of the artificial reef initial area, but also to assess the performance of the artificial reef for wave transmission, wave-driven currents, and wave breaking and surf amenity. So what's next? Well, we have a bit of an ongoing surf amenity assessment, or we're providing data to the City of Gold Coast, and I believe Griffiths University are going to use that data to assess that against the project. Had a set of key KPIs or key performance indicators. So this data is being provided by a surf camera that's been installed over the reef, and it's going to monitor and track wave breaking using the University of Queensland's algorithms. So that data will be used to by the Griffiths University to further analyse the surf amenity performance of the structure. Both over the KPIs for the reef had requirements over the reef itself, but also in the lee, and we've seen a lot of surfing happening in the lee since the construction of the reef. And also the detailed design of the Albany Reef has now been completed, and there's a link here that I will leave in the presentation if anyone wants to watch the project video that's just been released yesterday on the Albany Artificial Reef, which is still in the planning, hoping to be built stage. And a little bit just on that surf camera, this is a picture from the camera. It's on top of the Magnolia, one of the high-rise buildings on the Gold Coast Highway. It's a shout out to the City of Gold Coast for funding that camera and the data that's going to capture. Again, a shout out to the University of Queensland, Michael Thompson and Professor Tom Baldock, who are looking into the analytics of that data to provide the wave tracking information, and SwellNet for providing the camera. And yeah, we're just kind of coastal engineers along for the ride. So, all right, well that kind of wraps up my presentation for today. Yeah, any questions?
That's excellent, Evan. Thank you. Thank you very much for that. It's really, well, it's really interesting to see how our own loggers are used in anger, but it's really nice to see how all these technologies are pulled together in terms of the drone footage and the computer models, and then the actual physical models at that fantastic facility at the Water Research Lab down in UNSW, which is amazing to see, and it's great work they do, and so it's really nice to do that. So thank you very much for that. I'll open up the floor. If anybody has questions, by all means type them away, but by all means turn on your mic now and ask away. One of the things we find really interesting here is the interaction afterwards. So does anybody have any questions to put to Evan via the mic? While people are getting brave there, Evan, Dan, my colleague in Washington, has said, can you tell us a bit more about the data processing tools you use for the wave statistics?
Yeah, sorry, I sort of skipped over that. Well, firstly, I just go back to the planning of the exercise. We actually didn't know about the automated the setup tool that Stef has showed us in the presentation last week with Hannah. So had we known that, we would have used that because it was quite a bit of work to deploy all 7 of those. So we learned a lot last week, and it would have saved us some time because we were actually running a little bit late on the day. So yeah, we will definitely do that next time. But yeah, in terms of the data analysis, we do most of that in MATLAB. We took the raw data out of Ruskin, and that's very easy to get it into MATLAB. And then we've got we de-tided it, and we have a range of different wave burst analysis. We break it into, I think it was half an hour bursts, and we were doing continuous 16 hertz measurements. So we broke it into bursts, analysed those bursts for wave parameters. I can't remember exactly which process we use, but we tend to use like 3 or 4 different analysis tools and make sure we're getting good wave parameter results out of but yeah, D-tide, spectral wave analysis, wave by wave analysis to get all our wave parameters, and then quality control. That's why, as part of the quality control, that's why we picked up that those 2 sensors were not performing, and they were kind of removed from further analysis. So
yeah, excellent. James Fraserhurst has asked what why the max length of ride difference with the model.
Well, that's a good question. In the field, we actually saw people getting waves beyond the reef, and that's because they're skillful surfers, and so the model isn't able to predict that. So yeah, they just good surfers are able to almost link it up to the beach break. But yeah, so yeah.
Excellent. And before I come on to speed. Nashman's comment, staying with the model, Gail has asked what the resolution of your model was.
Yeah, that's also a good question. I think it was over the reef, it was like a 1 meter by 1 meter. And then it sort of got, we used a rectilinear grid with high resolution over the reef, and it was 1 meter by 1 meter with, we did test a whole range of vertical resolutions as well, but we ended up going with sort of coarse or two vertical layers, but we used a wave breaking approximation, which is really well implemented in Swash, and it saves a lot of runtime and we were very happy with the results. So yeah, 1 meter by 1 meter, expanding out to 3 meter by 3 meter, and yeah, two layers in the vertical.
Excellent. Okay. Yeah. So Nashwan picked up on the comment you made about the sensor you left for 12 months. and has asked whether you had any issues with sediment covering in the sensors, and I guess that's also biofouling as a whole.
When I said 12 months, we did check on it twice, I think, yeah, in that 12-month period, but it was the same sensor left there for 12 months. We did clean it up every time we checked on it. I think it probably would have worked. We do have some biofouling preventative measures, but so yeah, we did download it and check it every time we went to the island. It was a very remote place in Cocos Keeling Island, so but it didn't have any this wasn't in the same environment. It was on a reef top, and we had I don't have a photo of it here, but we had it kind of sat up above the reef top, and there's not much sediment accumulating on those reef tops. Any sediment gets washed straight off. So no, we didn't have any issues at that location with sediment, but we had designed the sensor to accommodate the typical sediment variations we see on those reef tops. But yeah, we didn't have any issues with that.
Yeah, okay, great. Yeah, and with the pressure sensor, because it is actually measuring pressure, you can actually mount them. So I don't know if you can see that, but it's upside down. And it still measures the pressure the same, so it stops the build-up of sediment inside, and we'd recommend that if people are working near dredging, for example. So
I guess to add to that, I wouldn't recommend doing 12 months in the surf zone, because that would not, no.
Absolutely.
You can design the hell out of the frame, and it'll still, it's very dynamic in the surf zone. So got a short-term deployments is probably better.
Yeah, absolutely. So Chris Drummond from UNSW has asked, or it's commented first, and I completely agree. Great presentation, Evan. But based on the measurements and observations that you took, do you think that the surfing amenity is better on the reef or on the sandbanks in the lee?
Well, that's a good question. I think we're really surprised, or not so much surprised, but we're encouraged by the amount of surf amenity improvements in the lee. It really does come down to the wave conditions, but I guess the good thing is it's complementary. When you have bigger waves with lower tides, you get great surfing over the reef. And then when the wave condition drops down, you can go snorkeling on the reef, and the wave conditions and a high tide, for example, so smaller waves and high tide, you get much better surfing conditions in the lee. So, and the two are pretty complementary, because in the bigger conditions, it's just too difficult to surf in the lee. So I guess it depends on the conditions, but because the waves are often small on the Gold Coast, the surfing in the lee has been a real bonus.
Excellent. Yeah, really good. So we'll look at wrapping up. I'll just finish quickly, if we can, with Andrew's question. Andrew Stanaland has asked, what are the real world changes to the adjoining Palm Beach, and has the implementation of reef enhanced or detracted from beach management issues? Which is probably quite a big question to finish on, but yeah, in a snippet.
Watch this space. Look, it takes time for the beach to adjust to the reef, and the good work that the Griffiths Union are doing, I'm sure we'll be looking to answer some of those questions. And obviously we're keeping an eye on it. But too soon to tell. But it's having an effect. But look, there'll be a keen interest in that, and I guess watch this space.
Awesome. All right, Evan. Well, thank you very much for your presentation. Again, really interesting. I do hope that you managed to tax deduct your paddleboard, swimmers and snorkeling gear, given you used it on a project like this. But that's comment, not tax advice. So no, that's excellent. A really good presentation. Thank you for that. And thank you everybody for joining. And we're moving away next week from coastal engineering type projects to hydrographic. So I do hope you can join us next week, and I look forward to any questions that you may have. By all means, click them through, and I can always forward them on to Evan as well if you can't find him by stalking the internet. So thanks, Evan, and thanks everybody, and we'll see you next week, hopefully. Goodbye.
Thanks, Evan. Bye.